everyone, I'm Jait Zakir and today I'm going to speak on the topic hydro turbine. Since the dawn of civilization, man has been trying to harness energy from various sources for his benefit. Our global energy sector over relies on fossil fuel, which is responsible for most of the global environmental degradation and climate change. Hydropower has been reviewed as the most feasible source of renewable energy to provide significant levels of global energy. The world is moving towards sustainable energy. So it is of utmost importance to understand one of the important components of a hydropower plant, the hydro turbine. Before getting into our topic, I'll first give a brief introduction to hydropower. Hydropower or hydroelectricity refers to the conversion of energy from flowing water into electricity. It is considered a renewable source of energy because the water cycle is constantly renewed by the sun. One of the first uses of hydro energy was for mechanical milling, such as grinding grains. But today, modern hydropower plants produce electricity using turbines and generators. For better understanding, I would like to show you all a small demonstration.
This is a model showing how hydroelectricity is generated. When the water flows over the turbine blades, the turbine spins, and thus water's potential energy or kinetic energy is converted into mechanical energy. The mechanical energy of the turbine is converted into electricity using a generator, and thus the bulbs glow.
In the generation of hydroelectric power, water is collected or stored at a higher elevation and led downwards through pipes or tunnels called penstocks to a lower elevation. The difference in between these two elevations is known as the head. At the end of its passage down the pipes, the falling water causes the turbines to rotate. The turbine in turn drives the generator, which converts turbine's mechanical energy into electricity. Transformers are then used to convert the alternating voltage suitable for the generators to a higher voltage suitable for long distance transmission. Some of the advantages and disadvantages of hydropower are stated here. Now, let us move on to our topic, hydro turbine. In hydroelectric power plants, water turbines are used as prime movers and their function is to convert the kinetic energy of water into mechanical energy, which is further utilized to drive the alternators generating the electrical energy. Turbines can be classified into two types, based on the type of flow and based on the action of water. First, based on the type of flow, turbines can be classified into four types. In the axial flow turbines, water flows along the shaft axis. In tangential or peripheral flow turbines, water flow is along the tangential direction. In inward radial flow turbines, water flow is along the radius. And in mixed flow turbines, inlet is radial and outlet is axial. Based on the action of water, turbines can be divided into two types. First is the reaction turbine. Reaction turbines are acted on by water, which changes pressure as it moves through the turbine and gives up its energy. They must be encased to contain the water pressure or suction, or they must be fully submerged in the water flow. Newton's third law describes the transfer of energy for reaction turbines. Most water turbines in use are reaction turbines and are used in low and medium head applications. In reaction turbine, pressure drop occurs in both fixed and moving blades. It is largely used in dams and large power plants. Second is the impulse turbine. Impulse turbines change the velocity of a water jet. The jet pushes on the turbine's curved blades, which changes the direction of the flow. The resulting change in momentum or the impulse causes a force on the turbine blades. Since the turbine is spinning, the force acts through a distance, and the diverted water flow is left with diminished energy. An impulse turbine is one in which the pressure of fluid flowing over the rotor blades is constant and the work output due to the change in kinetic energy of the fluid. Prior to hitting the turbine blades, the water's pressure or potential energy is converted to kinetic energy by a nozzle and focused on the turbine. No pressure change occurs at the turbine blades, and the turbine does not require housing for operation. Newton's second law describes the transfer of energy for impulse turbines. Impulse turbines are often used in very high head applications. Now, I would like to discuss about some other important types of turbines. First is the Pelton wheel turbine. It is an impulse turbine and is suitable for high head and low flow plants. The potential energy of water in the penstock is converted to kinetic energy in a water jet issuing from a nozzle. It consists of a rotor equipped with an elliptical bucket along the periphery of the turbine. Majority of the Pelton turbines are of horizontal shaft type. Impulse turbines have long penstocks due to high heads. This turbine is not suitable for waterheads below 200 meter. Next, let us move on to the Francis turbine. Francis turbine is an inward mixed flow type of reaction turbine and is suitable for medium head and medium flow plants. Such turbines develop power partly due to velocity of water and partly due to the difference in pressure acting on the front and back of the runner buckets. The full load efficiency of this type of turbine is about 92%, but with part load the efficiency decreases to 65% at half full load. Francis type turbines can be constructed in vertical and horizontal forms. The alternator is mounted above the turbine and thus is free from flooding. This turbine can be designed for a higher speed than Pelton wheel. Third is the Kaplan turbine. Kaplan turbine is also a reaction type turbine and has gate and governing mechanism similar to that of a Francis turbine. The difference between Kaplan turbine and Francis turbine is that in the former, water strikes the turbine blades axially, whereas in the latter, water strikes the turbine blades radially. Water flows radially inwards through the regulating gates all round the sides, changing direction in the runner to axial flow and causing a reaction force which drives the turbine. Practically, all Kaplan turbines are of single runner vertical shaft type. Kaplan turbine, because of its highest specific speed, is suitable for low head and large flow plants. Kaplan turbine gives high speed than ordinary Francis turbine, resulting in the lower cost of runner, alternator and the powerhouse structure. Its efficiency is about 90% at all loads. The special feature of Kaplan turbine is that its runner is capable of reverse operation as a pump and is therefore ideally suited to pump storage plants. Last is the propeller turbine. It is an axial flow reaction type turbine and has got no provision for changing the runner blade angle while the turbine is in motion. Though its construction is simple and easy, but its efficiency falls sharply at reduced loads, and therefore such a turbine is kept fully loaded for efficient operation. Its efficiency is about 92% at full load. Now, let us discuss the components of turbine. The water from above the dam flows down through pipes called penstocks. At the end of penstock is the spiral case. This curls around the turbine like a snail shell. It is designed to distribute the water equally in all directions of the turbine. It is of progressively decreasing cross section to maintain constant velocity of water. The inside circumference of casing has stay rings and stay vanes, shaped to guide water properly to the guide vanes. The steering is designed to support the weight of the superimposed structure, the spiral casing, and the pressure gauge. Inside the spiral case is a set of vanes called the wicket gates. These control how water flows into the turbine. The wicket gates are controlled by an external governor system. This opens and closes them in response to the conditions on the national grid. A high load on the system slows the turbine, and the governor system reacts by opening the gates further to speed it back up. Conversely, it will narrow the wicket gates in response to the low load on the system. Beyond the wicket gates, we can see the turbine blades. The turbines are shaped to extract the most possible spin from the moving water. The turbine blades and the shaft connecting them to the generator are called the runner. The runner transforms the hydraulic energy into mechanical energy. The blades, four in number, are fixed to the runner hub. The runner blade servo motor is housed within the hub, which in turn is fixed rigidly to the shaft. The runner is designed to withstand the forces due to runaway speeds and to support its weight and the weight of the main shaft when the latter is disconnected from the generator. The main shaft, vertically aligned in the powerhouse, transmits rotational energy of the runner to the generator. The shaft is designed to operate safely in combination with the generator shaft without any detrimental vibration or objectionable distortion. Next, the main guide bearing is the one which provides radial support to the main shaft. The draft tube is a pipe of gradually increasing area of cross section placed at the exit of the runner. It is used to extract the energy from water leaving the runner and hence increase the turbine output. It is of elbow type construction and has a circular entrance and a rectangular exit. Last but not the least, the governor. It consists of an electrical equipment cabinet and a hydromechanical actuator. A speed signal generator connected to the main shaft produces signals of a particular frequency at the particular rated speed. When the speed of the unit changes, the frequency of the SSG also changes, whereupon a discriminator responding to the frequency variations emits an electrical signal. After being amplified, the signal is finally transformed into a mechanical displacement transmitted to the main governor valve. Accordingly, the guide vanes are opened and closed along with the simultaneous movement of the runner blades. Now, let us move on to our next topic, turbine auxiliaries. The turbine requires various auxiliaries for smooth running and function. Let us discuss some of the turbine auxiliaries. First is the oil pressure unit, used to provide oil at high pressure required for governor operation, guide vane servo motor, runner servo motor, and cooling purposes. Second is the hydrostatic lubrication system, which is used in the generator to provide an oil film between the thrust pads and the runner during the starting and stopping of the operation. The brake jack system is used when HS lubrication is not working. In that case, the rotor shall be jacked up and released through the brake and jack panel just before starting the unit to ensure formation of an oil film. Fourth is the air compressor unit, which provides compressed air required for generator air braking, charging governor oil pressure tanks, and for service station applications. Fifth is the cooling water system, which gives the required cooling to maintain the temperature rise in various parts of the machine within limits. The most affected parts being the generator bearings, generator windings, shaft seal, etc. Lastly, a drainage system is provided to the units for collecting and discharging of various leakage and seepage in the generating units. And a dewatering system is provided for dewatering the turbine space, spiral case, and the draft tube section when the unit is taken out for maintenance. The specifications of hydro turbine are stated here. The approximate price of Francis and Kaplan turbine is shown in the table. I would like to conclude by saying a transition to clean energy is about making an investment in our future. Thank you.